Okay, so I'm just going to show you how to analyze projectile motion. So let's say, for example, we start off with our simulation, and our simulation says we've got a cannon launching a cannonball at an initial speed of 14 meters per second. And if you can kind of make it out there, it says 53 degrees as the angle that I set. I chose that angle. Okay, so this is just a picture. Okay, so the first thing to do, once you've done that, once you've got your question, is to break down your vector into its components. So I'm taking the initial velocity u, I take my angle, 53 degrees, and I use u cos theta for the x component and u sin theta for the y component. That gives me uy equal to 11.18 meters per second and ux equal to 8.425 seconds. Okay, that's step one. Just break it down that further. So step two is to list your data separately. Okay, so you split it into the x column and the y column. Okay, I use a subscript for x for my x data and a subscript for y for my y data. So my initial velocity in the x direction is 8.425 meters per second. The horizontal range is unknown, Sx, and the time is unknown. We do know that the time for x is the same as the time for y, so we're just going to drop that x and y notation and just call it t. Okay, just make things a little bit easier. I then list my y data separately. So I've got the initial velocity in the y direction is at 11.18 meters per second. Now I've listed here that the final velocity is negative 11.18 meters per second. I don't want you to list that necessarily, okay? I want you to be able to get to that, because that won't necessarily always be the case. If there's a height difference between where it's being launched and where it lands, then that won't happen, okay? So the method I'm just going to show you involves solving for the final velocity first in the y direction and then working from there. So that's the technique I'd like you to use. We've got the acceleration is negative g. The change in y for in this case, and in most cases is known. Okay, in most cases is known. So the change in y is going to be 0 because it's going to come all the way up and then come all the way back down again. And again, time is the same for x as it is for y, so again we just call that t. Now please note that in the top of that corner there, I have shown my frame of reference. So anything that's pointing up, I'm applying a positive sign to. Anything that's pointing down becomes negative. Right, I'm taking to be positive. Left, I'm taking to be negative. Okay, that's step 2. Okay, on to step 3 now. So step 3 is basically, what we're going to do for step 3 is basically what I just said a moment ago, which is we're going to make sure that we always solve for the final velocity in the y direction first. Like I said, if in the special case where the displacement in the y direction is 0, then the final velocity in the y direction will be the negative of the initial velocity in the y direction. Okay, well, like I said, this may not always be the case because there may be a height difference between where you start and where you finish. So I'm going to apply this formula. Notice everything carries a subscript of y. So my final velocity in the y direction squared is equal to the initial velocity in the y direction squared plus twice the acceleration in the y direction times the change in position, or the displacement in the y direction. So just like we did in the example today, when you plug in your numbers, because the displacement in the y direction turns out to be 0, you wind up with the square of the velocity in the y direction, the final velocity, be equal to 11.18 meters per second squared. Take the square root, but don't forget that this could be positive or this could be negative. So here's where you have to use a little bit of common sense to realize that you have to take the negative velocity, because obviously it's on its way back down. Okay. Okay, so on to step 4 now. So once we have the final velocity in the y direction, we solve for the time. Okay, and that's the technique we will always use. So the final velocity in the y direction is equal to the initial velocity in the y direction plus the acceleration in the y direction times the time. Okay, rearranging for the time, you get v minus u all divided by the acceleration. That gives us a negative 11.18 meters per second for the final velocity, minus plus 11.18 meters per second, because that was the initial velocity. So minus times plus becomes minus. And then divided by the negative acceleration. Now, you should always expect your time to be negative. Okay? Time will always be negative in these calculations, otherwise you have made a mistake. Go back and double check. Okay? So now we're on to step 5. Step 5 is once you've got that time, all you're going to do is you're going to apply basically distance, speed, and time. Okay, distance, speed, and time, or displacement times velocity. Displacement equals velocity times time. Okay, so you're going to plug in your time there, and you'll get your displacement. Okay? The displacement in this case worked out to be 19.2 meters. Now, once you're done with this, I want you to use the simulation that I posted on the site to check your answer. Let me show you what I mean. So, I'm going to just come out of this for a little sec. I've predicted that my position is going to be at 19.2 meters, so I'm going to catch this little thing out here. I'm going to pull it out to 19.2 meters, and I'll press fire. If I've done it right, it should hit it on the bullseye. Boom, there you go. So all you do is, to practice these, is you reset the simulation, change the angle to whatever you want. You can change the initial speed to whatever you want. You can turn it up, you can turn it down, and then you run through the same stuff again. Leave everything else on the side, because there's controls here on the right that you can't really see right now. Leave all that okay. And by the way, the version of the simulation that we're using for this is the lab one. You see it on the bottom corner. Don't use the drag one because you'll get air resistance into it. Leave air resistance off on this. Okay. Now, once you've got that done, you should do one more thing, because in order to fully understand what happens in these projectile motion situations, I want you to graph it. Okay, I think graphing makes things very, very clear in your mind as to what's happening. So I've got my graph laid out on my y-axis. Sorry, this is the velocity time graph. So I'm going velocity in the y-axis, velocity y on the y-axis, and time on the x-axis. Then I'm going to do a separate one here for the velocity in the x direction, and the time again on the x-axis. So what I'm going to do is I'm just going to graph it out. So I'm just going to add a line to this, and start up here at my initial velocity, which is 11.18. Misbehaving, unfortunately. And it should pass through this line here. That's about 2.27 meters per second. And I'm going a bit too far. So around there. Okay. Oh, my apologies. My apologies. In order for me to do this, what I need to do is I need to go to, 2.27 would be the final time. 2.27 would be the final time. Okay. So it'll be around there. That's what it should look like. Okay. So hopefully you can see that. Please notice that it cuts the the velocity time graphs for these situations is always going to be the same. Okay, it's a straight line that comes down like this, and it kind of runs and maybe a little bit counterintuitive. Maybe the first couple of times you see it, but once you do it out a few times, you'll be good. Okay. Now, what I would like you to check is that the area here should give you the displacement that is on the way up. Okay. Now, I'd like you to check that by using the area, calculate the displacement from the area underneath the curve, but then set the final velocity in the y direction, v final y, equal to 0, and solve for the displacement, and you should get the same answer. Okay. Then one more thing. This is the displacement for the second part of the question, or for the down part. Okay, it's the displacement between the line graph and the time axis. Okay, because I know this always confuses students. Where do I take my displacement? Am I taking it here? Is it all of this area here? No, it's the area between the line graph and the time axis only. Okay, so your eye must always be drawn back to the time axis. So I'm looking at this area, and I'm looking at this area. So this is the area that's going to be coming down, or the displacement down. This one down. Now you can kind of tell from the graph that the up area is going to be a positive area, whatever that gives you. I'm not really sure. You can work it out and check yourself. But the down one is going to be a negative one, because you're going to have a negative velocity when you go to the top of the triangle, which is here. Okay. Your time interval will be exactly half of this value here. Okay, so 2.27 should be around 1.135 or so. Okay, which is supposed to be around here. I might be a little bit off on my graph, but the net displacement in the y direction will be 0. Okay, because whatever it went up by, it came down by the same amount. Okay, so let me just quickly show you then the x1. So for the x1, what we do is you take your, you're going to graph this one. Again, I've put my scale. I might zoom in a little bit so you can see a bit better. I'm going for 2.27 seconds, and I'm going from the initial velocity in the x direction, and it's a flat line from there all the way to here. Okay, so that's what I want you to do. Okay, I want you to solve for the horizontal range basically in every practice one that you do. So you can select the velocity, you can select the angle, change them every time, and on the simulation this thing goes up and down as well, just to let you know. So if it's up here, our frame of reference is taken from this point, which means right now I'm at 5 meters above ground level. If I'm starting from 5 meters above ground level, that means when the ball hits the ground, the displacement in the y direction will be negative 5 meters, because I put my frame of reference right here. Okay, so it will be negative 5 meters. That's where people get caught on this as well. Okay, so just remember, if this thing, if the cannon is being launched higher than where it's landing, then your displacement will always be negative in the y direction. Okay, so best of luck with that, and let me know how you